Okay, this is Algebra 2 4.4, Properties of Logs. So just like exponentials have properties, logarithms do too. And logarithms don't have quite as many properties as exponentials either. Our joke for the day is the teacher asks, what are some properties of logs? And the student is thinking quite differently, and they're saying they're round, they have bark, and they come from trees. But no, the teacher is thinking of things like stuff on this page. It's, yeah, we already talked about that a little bit. So if you think back to when you have exponentials, if you are multiplying two exponentials, you would add their exponents as long as the base is the same. So the product of the exponentials is a sum when you add them. But with, and there's also a similar one with the product property of logarithms. So when you have the log base b of a product, m times n is a product, that's the same thing as log base b of the sum. Log base b of m plus log base b of n. And that's also called expanding. So on the left-hand side, that's considered condensed form. And on the right-hand side, it's considered expanded. So you'll have to memorize this property, and a way to help you to memorize it is you can say the log of a property, the log of a product, sorry. The log of a product equals the sum of logs. And that can help you remember what the property says. There's also, so we're going to do an example first, actually. Okay, so this is how we do this. So they give this is actually an expanded form, and so we're going to go the other way and condense it. So just since we just learned the property, let me write it down again. Log base b of mn equals log base b of m plus log base b of n. Okay, so we're going from the right-hand side back to the left-hand side. So we can only do this because they're both log base 4. If they were different bases, you wouldn't be able to combine them. So we know because we have a sum, it's going to be the log of a product. So it's going to be log of 2 times 32, which is log base 4 of 64. And then it does say to simplify it if we can. So we ask ourselves 4 to what power equals 64? And that's 3. These are a couple that you can do on your own. Alright, so on this one we have a sum, so that means it's going to be the log of a product, because they're both base 5. 625 times 25. And that's going to give us a rather large number. Let's see. I'll just do it on my calculator here. 625 times 25 is 1,500, Now, to simplify that, it's actually kind of worse than originally. Like the original ones you can do in your head more easily than you can do this one. So I would say it's kind of simpler to come back up here and do them individually. So 5 to what power equals 625? Again, you'd have to guess and check if you don't know what it is. You could try 5, it's obviously not 5 squared. 5 to the third is 125, and then if you multiply 125 times 5, you'll get 625. So it ends up being 4 plus, and then log base 5 of 25 is 5 to the second power would equal 25, so that's 2. So it's equal to 6. So that means that 5 to the 6th power is 15625, and you can check that on your calculator and see that it is correct. Okay, this one, again, it's a sum, so we can write it as the log of a product. 27 times 1/9. So we can simplify that. If you prefer, you can do it that way. So it's going to be 27 over 9, which is 3. So log base 1/3 of 3. And then you can ask yourself 1/3 to what power equals 3? And because these are reciprocals of each other, we know the power has to be negative. And in this case, it's -1, because 3 to the 1 would be 3. So 3 to the negative, 1/3 to the -1 would be 3. Now we're going to do a second property of logarithms called the quotient property. And when you do a quotient of exponentials, you subtract the exponents. When you do the log of a quotient, it'll be this difference of the logs. So we'll be subtracting as well. Log base b of m minus log base b of n. So what you could say outside is the log of a quotient is the difference of logs, if that helps you memorize this better. And then we'll do an example using this. Oh, and by the way, back on that other slide, on the left it's condensed, on the right it's expanded. And you can flip back and forth between these forms. So on this one, they're giving us the expanded version, and then we're going to condense it into a single logarithm. So let's write the property down again where we can have it handy. So I know that because this is a difference of logs, it's going to be the log of a quotient. So log base 2, and then it's the first one that appears goes on top, and the second one goes on bottom. Log base 2, 32 divided by 4 is 8. And then you ask yourself 2 to what power equals 8, and that would be 3. And we have simplified it. So make sure when you're doing these that you keep going all the way until you can simplify it as much as you can. Alright, and you can try this one on your own. So again, this one's expanded. We're going to need to condense it. So it's going to be the log base 7 of the quotient, 49 divided by 7. That's log base 7 of 2. Or no, it's not 2. Getting ahead of myself. 49 divided by 7 is 7. There's no 2 involved whatsoever. And 7 to what power equals 7? That's 1. So log base 7 of 7 is 1. Sorry. And then this is the third property. This is called the power property, and this one's kind of interesting. This is when you have the log of a power, we can actually bring this exponent p out front and multiply it to log base b of a. So with numbers, if you had log base 3 of, I don't know, 8 to the 4th, for instance, that's the same as pulling the 4 out front. 4 times log base 3 of 8. And likewise, if you have a number out front being multiplied to the logarithm, you can bring it up and make it an exponent here. So this 4 can come back up here. So you can switch back and forth between the two forms. The one on the left is condensed. The one on the right is expanded. Our book doesn't use those terms per se, or I don't recall that they do, but it's something we use in pre-calc, and it's something I end up saying. So here are some examples that you can try, or we'll do these together. So log base 3 of 81 to the second, that 2 can come out front. And you have this. And then you can do log base 3 of 81, because 3 to what power equals 81. If you don't know what it is, you can do a little bit of guessing and checking. But 3 to the 3rd is 27, so if you multiply 27 times 3, you're going to get 81. So then 3 to the 4th is 81. So you end up with the 2 still out front times 4, and you get 8. Over here, I'm going to bring the 3 down in front, because it's a power there. Log base 5 of 1/5. 5 to what power equals 1/5, and that would be -1. So 3 comes down, multiplied by -1, and you get -3. Okay, do these on your own. Okay, so we got 4 coming out front. And This means 10. There's a base of 10 here, so 10 to what power equals 10? And that's 1. So 4 times 1, 4 is your answer. This next one, we're going to pull the 2 out front. Log base 5 of 25. 5 to what power equals 25? And that's 2. So we've got 2 times 2, which is 4 again. Okay, we'll pull that 5 out front. 2 to what power equals a half? Because that's a reciprocal, it's going to have to be a negative 1. So 5 times negative 1, negative 5. Okay, so those first three properties we've learned help you manipulate and change logarithms and rewrite them. The inverse properties actually help you solve logarithms. And there are 2 of these properties. And this, by the way, this one has a little b here, log base b. So this first one is log base b of b to the x. So I'm going to come over here and do the work, and then I'll fill in the answer there. So we can use the power property we just learned and pull the x out front. And b to what power equals b, that's 1. So log base b of b is just 1. So x times 1 is x. I believe in the last section we learned that log base b of b is 1. That was one of the properties we learned last time. Or you can just think about it too. And then this one, trying to think if I know of a good proof or explanation for this one. The best I can say is you have an exponential base, b raised to a power, and then you're raising it to a logarithm base b, and those are inverses of each other. They undo each other, and when they undo each other, they just kind of wipe each other out, and you just get x. So b raised to log base b of x is just x. You can see how these inverse properties are helpful because they greatly simplify things, and that's why we use them to solve and undo. And then we'll use them here on this example. So I'm going to break down that 3x plus 1 out front and put it in parentheses because I'm going to be multiplying it to log base 8 of 8. Log base 8 of 8 is 1, so 1 times 3x plus 1 is 3x plus 1. This one, what you could do, you could just do 5 to what power equals 125. Or if you wanted to, you could say log base 5 of 5 to the third, because 125 is 5 to the third. You could write it this way, and then bring the 3 out front and write 3 times log base 5 of 5. And log base 5 of 5 is 1, so you get 3. Or you might have just looked at it, like I said, and just said, okay, I know that that's 3. 5 to the third is 125. On this one, when the 2 raised to the log base 2 it's gonna wipe itself out there, and you're just left with 27. Okay, here's some more to try on your own. This one, this is again log base 10, because it's understood it's the common log. And so when you have log base 10 of 10 to the 0.9, you can just simply use the property and realize that these are going to cancel out and it's just 0.9. If you don't recognize that property, you can take the 0.9 out front. And then notice that log base 10 of 10 is 1, and so 0.9 times 1 is just 0.9. So if you notice and recognize the property, which hopefully you will, you can just go directly to the answer right away. And on this one, it's the same deal. You can notice right away that 2 raised to log base 2 cancels out, and you just get 8x. Okay, now there's something called the change of base formula, and it's actually a very handy thing because you can use it to find the logarithm of anything on your calculator. Because at this point, the only ones we know how to do on our calculator are log base 10. I don't even know we've talked about that yet. Like for instance, if you want to go on your calculator, I have to call it up. Whoops, I hit the wrong button. Oopsie. I'm sorry, I can't recall whether we already did these before or not. But say you wanted to find log of 42. That means log base 10, and this log button is log base 10. It's understood to be log base 10. So if I did log of 42, I would get whatever that power is. Let me check one that we can do in our head. How about log of 100? Okay, what does that equal? Well, that's 10 to what power equals 100, so that would be 2. So on the calculator, if I do log of 100, I get 2. So this log button on the calculator is only base 10. But the change of base formula will enable us to use that log base 10. So anyway, if you have log base b of x, you can rewrite that as log of x over log of b. And that's base 10, because these are understood to be 10s. So that's the same. These are 10s here. The thing to remember is that you have to remember which one goes on top. And already in this right here, the x is slightly above the b, and the x goes on top and the b goes down below. You can actually rewrite these using any base you want. So you could do log base 2 of x over log base 2 of b. Or you could do log base 5 of x over log base 5 of b. You can use any base you want as long as the base is the same. So in general, you can do log base a of x over log base a of b. And we use this one a lot because we can use our calculator, the log base 10. So this one is quite popular. That's the one we use on our calculator. And these ones are handy when you're trying to do things in your head, as you'll see here on one of these examples. So this first one, we'll do it using a calculator, change to base 10. So using the change of base formula, it's going to be log base 10 of 8. 8 is up on top, and then log base 10 of 4 on bottom. Then we go to our calculator. So we would do log of 8, close the parenthesis, divided by log of 4, close, enter. And that's 1.5. Okay, now if we wanted to do it in our head, we actually could on this one because 4 and 8 are both powers of 2. So we could choose log base 2. And that would be log base 2 of 8 over log base 2 of 4. Because we can do these in our head. Log base 2 of 8 is 3. 2 to what power equals 8? That's 3. And then 2 to the second would be 4. Ah, look at that. We get 3/2, which is the same as 1.5. Okay. These you want to try them on your own. Try to figure out what base you would use so that you can do them by hand. So this first one, 9 and 27 are both powers of 3. So I'm going to use log base 3. 27 is on the top. Log base 3 of 9 would be on the bottom. Log base 3 of 27 is 3 to the third would give you 27, so that's 3. And then 3 squared would give you 9. Oh, that's 1.5 again. On this one, 8 and 16 are both powers of 2, so I would use log base 2. 16 on top, log base 2 of 8 on bottom, and log base 2 of 16 would be 4, 2 to the fourth is 16, and the bottom one would be 3, so this one's 4/3. And we're on the last example. This is a long example. It shows up a lot. We use it. Seems like our book really did a lot of these, so it's important to follow along and try to learn it. Seismologists use the Richter scale to express the energy or the magnitude of an earthquake. The Richter magnitude of an earthquake, M, is related to the energy released in ergs, which is kind of a funny word, E. So E is ergs, which represents the energy, and then here's the formula that relates them. and it's a logarithmic formula, so that's why Richter numbers are so funny. Like a magnitude 9 earthquake is significantly larger than a magnitude 8 because it's a logarithm, so they're not linear. In 1964, an earthquake centered at Prince William Sound, Alaska, registered a magnitude of 9.2 on the Richter scale. Find the energy released by the earthquake. So first we have to decide where the 9.2 goes. And if you look back up in the problem, it says the Richter magnitude is M. So the 9.2 is the M. So we'll put that in our equation. Like so. And we're trying to find energy, so we're solving for E. We need to get E by itself, and right now it's stuck inside that parenthesis. The first thing we can do is get rid of the 2/3. So I'm going to multiply both sides by 3/2 in order to get that over here. And 9.2 times 3/2, that's 1.5 times 9.2 is 13.8. That cancels. Then we get log of E over log of E over 10 to the 11.8. This is the log of a quotient. So what we're going to do is we're going to do the use the properties, the log properties, and rewrite that as the log or the difference of logs. So that's the same as the log of E minus the log of 10 to the 11.8. So I used one of our properties to rewrite that. Now I need to solve for E, so I'm getting a little closer here. This log, oh, by the way, because this is a common log, it's base 10, so I could think of that as being log base 10 of 10 to the 11.8. Ah, I recognize a property there. These are going to cancel out. This is just 11.8. So let's bring everything down. This whole thing right here is just 11.8 because we were able to use one of the inverse properties to simplify it. Now we can add 11.8 to both sides. And that's going to be 6.1. That's going to be 256. Right, 13.8 plus 11.8. Yep, 25.6 is log E. Wow, but we still haven't found the energy yet. But we're almost there. Again, this is log base 10, and what we can do at this point is we can rewrite this as an exponential, like we learned in the previous lesson. This is an exponential with a base. It's 10 to the 25.6 equals E. And then we can do that on our calculator. 10 raised to the 25.6 is 3.98 times 10 to the 25th. I think I'll do that so that you can see how I got that. We'll do that here. So I did 10 raised to 25.6. And make sure you look over here to the right where there's this E25, that means times 10 to the 25th. And then also you should write the units, which are ergs. I don't know what the symbol is, so I'll just write ergs. And since we don't know what an erg is, we don't really have an appreciation for just how much energy this is. But if we were seismologists, we probably would. And we've heard about the destruction of the earthquake, so we know it was very large, very, 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 very large. Okay, I think we'll probably do one of these in class again, so you can practice this as well.